Hi everyone, Happy New Year! I'm going to briefly tell you about the work that my undergraduate students have been doing to investigate what we can learn about the 2018 Kilauea eruption from seismic anisotropy. Now, seismic anisotropy is when seismic energy travels faster in one direction than another. In the Earth's crust, there are microscopic cracks in the rock, and when the rock is under a differential stress, the cracks parallel to the maximum compressive stress will open, and those perpendicular will close, creating an anisotropic medium. When a shear wave travels vertically through the anisotropic rock, the energy aligned with the cracks will travel faster, and therefore the wave will split into two. This is called shear wave splitting, and its detection is one of the best tools for monitoring in situ stress. However, there are other factors that can cause seismic anisotropy, such as pore fluid pressure or macroscopic features like aligned faults. So with this in mind, our team has set out to investigate four really interesting aspects of the 2018 Kilauea eruption. Firstly, we investigate the start of the eruption. Before the 2018 sequence, there were two open vents, Halemaumau in the summit caldera and Pu'u'o on the East Rift Zone. There have been two opposing models published to explain why magma withdrew from these open vents. So to test these models, we look for changes in shear wave splitting parameters in the months to weeks preceding the start of the activity. Only 6 days later, a magnitude 6.9 earthquake occurred off the southeast coast of Hawaii. Other authors have modelled stress transfer between the intrusion and the décollement, and back again. So we use shear wave splitting to see whether this stress transfer can be seen. Meanwhile, at the summit, magma drained from the reservoir, removing the support for the caldera floor, and this resulted in an incremental caldera collapse. Here we use the unprecedented seismicity catalogue and dense seismic network around the caldera to image the evolution of cracks as the caldera collapsed. And finally, after 3 months of increased seismicity, caldera collapse and high lava effusion rates, the activity rapidly declined on the 4th of August. We investigate whether we can detect changes in stress in the lower East Rift Zone associated with this anomalously fast termination of the eruption. So please come along and have a look at our poster to see our results.